well, there's African
It's
tribes.
still complaining.
Or using talking drums.
But only at the beginning. Once we get past the first part, it's okay. So we'll just keep an eye on it, and then, from time to time, just to make sure that we are not messing up the entire thing.
It doesn't dump out in the middle of it. So it doesn't dump out in the middle of it so that you know.
Right. So let's go ahead and get started with today's lecture. And I'm going to move my row sheet into my view, just so that I can see it. And I drew a little Darth Vader on it. So I'm hoping that will help remind me. All right. So are there any questions about the homework assignment other than the spelling mistake of
Can we use the fill instruction to replace the content of
What do you mean by replace?
So if you've got some values stored in a memory address,
Right.
and you want to change those values,
No, the thought field thing is more of a static thing. It's quote unquote equivalent to initialized variables in a C++ program. So it's only useful when you're starting a program, but when the program is running, dot field doesn't do the same. So you cannot quote unquote activate dot field when your program is in execution.
okay.
If you do want to zero out a section of memory, you will have to write the code to do it. Yep. I'm sorry, go ahead.
It does have a fill command, so you can specify a value and how much and how many repeations of that character.
You mean the dot fill?
Yes.
The dot fill is a directive, which means it is instruction to the assembler itself, so that when it puts a program together, there's a section of memory that is quote unquote marked as initialized, and it will just basically load a whole bunch of zeros into that memory location before your process starts, before your program starts executing.
Oh yeah, I was saying instead of 0, you could have a different value as well.
Yes, you can. Yep, you can. So the way dot field works is you can specify count. You can also specify how big is a chunk and what is the value of each chunk. So it can take on those additional parameters. But as far as your homework is concerned, it is easier to use restore to load known content into the memory space than to use dot field to do it. Besides, you can load up your different test cases too with the restore function. Okay. Any other questions? Yep. Mm-hmm.
The values are bytes, correct?
The values
That we're searching for, those are bytes.
Yes, so we are looking for 5 individual bytes, and those are the ASCII values of B, U, N, and Y.
Okay.
Or, since I misspelled it in the homework assignment, B, U, U, N, Y. So I'll be, you can look for either 5 character chunk, and it will be considered correct.
So when we're doing comparisons or arithmetic with those, we should always be doing it with other bytes, correct?
Okay, there are 2 types of compares that you need to use in this particular program. So keep in mind that when you work with characters, 1 character is only 1 byte. Okay, so that is one thing. The second thing is, because we are dealing with a 32-bit architecture, so the address, each address is a 32-bit thing.
Right.
So you have to choose the right width of operation and the right width of register, depending on what you do.
Whether you're working with the address or the bytes.
Or the content at the address. Correct. Yep. And that's one of the main points of this homework assignment, is to make sure that you guys can differentiate what is an address and what is the content at the address. Are there any other questions? No other questions? I'm assuming most of you have started with the homework assignment. Okay, all right. So if you guys can think of any questions, along the way, just keep, asking those questions. And what I'll do today is I'll go over a few examples of how to combine conditional branch instructions, just to do kind of funny things. Okay, not funny, but it's useful stuff. That needs to be talked about. All right. So getting back to the lecture, we are now in the really big section, assembly language programming. And at this point, we are done with subtracting and comparing. Okay, that's basically your CMP or compare instruction. Your subtract instruction, SUB, the only difference is one will store the result into the second operand and the other one does not. But both will affect the 4 flags that we need to use for most of the control structures. We are done with arithmetic operations, okay, which is at this point just basically addition and subtraction. Okay, are there any questions? Any questions? Okay. Yep, go ahead.
So subtracting and comparing, it's like comparing two value of two registers and say 2 as equal.
Not okay. The best way to explain is first the subtraction instruction. The subtraction instruction will subtract the first operand from the second operand, and then store the difference, the result, in the second operand. The second operand is always the destination. That's where you store something. The compare instruction is just like a subtraction, except it does not store. So it will go through the same motion as a subtraction, except it does not store the result. It will change the flags just the same though. So it will still affect the 0 flag, the carry flag, the overflow flag, and the sign flag. Are we okay with that concept? Yep.
Does the sign flag reset itself automatically?
The sign flag, quote unquote, does not reset itself. It will be changed the next time you have another add instruction or subtract or compare instruction.
Okay.
The move instruction does not change the flags. So you can have as many move instructions as you want or jump instructions. Those do not change the flags. But whenever you have an add instruction, a subtract instruction, or a compare instruction, they will overwrite the values of the flags. Are we okay with that, with those concepts? Which basically means, if you have a compare in your code, you probably want to use a conditional branch like right after, okay? Because it doesn't make sense otherwise. Okay. Any other questions about these instructions? No questions? Right. So if there are no questions, I'm going to go back here and talk about what else we have gone through. We have gone through some of the jump instructions, not all, but the most basic ones we have already gone through. Yep, go ahead.
So what does conditional branch mean in this sense?
Say again?
What does conditional branch mean in this sense? It's like another.
A conditional branch is a JC, JNC, JZ, JNZ, JO, JNO, and JS, JNS. Okay, so those are the 4 pairs of really basic conditional branch instructions. But in addition to those, okay, because we're dealing with a cisp architecture here, we also have complex conditional branch instructions that make use of multiple flags and not just one at a time. Okay, so let me just kind of talk about this with a mouse pad. And since I think everybody who's going to be here are here already, I'll just pass the row sheet. And I make sure that part is recorded, well, obviously. Yes. Okay, so we'll take a look at the branch instructions that we have talked about so far. All right. So we have branch instructions corresponding to all the flags that we have talked about. We have JC, which means branch if and only if the carry flag is set. That's JC. JNC is the counterpart of that, which means branch if and only if the carry flag is cleared, reset, 0, okay? And so it will branch to whatever label you specify, but only if the carry flag is cleared. In this case, if the carry flag is in fact, a 1, it will just continue with whatever instruction is next to it. Are we okay so far with the concept of a conditional branch? It's not like in C and C++ with a conditional statement where you can say, hey, if it is true, go here. If it is false, go there. Okay? You can only control where it goes when the condition is true. If it is false, it just kind of falls through to whatever is next to it. Are we okay with that concept? Because that's going to be the building block that you have to use in order to implement most of the complex control structures. So we have JC, JNC, JZ, JNZ for the 0 flag, JO, JNO for the overflow flag, and then we have JS and JNS for the sign flag. These are the most basic ones. But sometimes it might come in handy and say, well, but I don't really want to know whether the overflow or the sign flag is set or cleared. I want to branch after a signed comparison, and if the first operand is less than the second operand, I want to go somewhere. Okay, so let's take a look at this instruction here. Okay, so we'll take a look at this one here. We'll move say -1 into EAX, and then we'll do a compare long, and this is going to be a signed comparison. So I want to compare 1 with EAX. And I want to say J something to, let's see, I want to use, the first operand has to be greater than, okay, so a label called greater than, and the label greater than is here. And then what happens, if I continue execution here, is basically less than or equal to. Okay. When I use less than or equal to, greater than, or any type of comparison, I am basically saying, in this case, the second operand is less than or equal to the first operand. Okay, so the order of reading this is kind of reversed. You have to be careful about that. Okay. All right, so the question now is, what do I use here in place of the question mark so that I would end up at the label greater than if EAX is greater than 1. Okay, so just think about this as some other unknown. Okay, so this way it's easier to demonstrate. So what happens when the question mark is greater than 1, and I want to end up at the label greater than, instead of continuing execution with whatever is after the conditional branch instruction? Well, what do you think?
So when you want to jump when the content of EAX is greater than the
Than the value of 1. But it has to be a signed comparison. It has to be a signed comparison, so -1 is considered less than 1, and 2 is considered greater than 1. Okay? All right.
That compared to what the sign bit would be.
Well, this kind of goes back to an earlier discussion. This is like from weeks ago, so I'm hoping some of you still remember. The less than flag is the sign flag, or usually at least the overflow flag first, exclusive or the sign flag. Do you guys still remember this one? Because we have to look at both the overflow and the sign flag in order to determine which value is larger and which one is smaller. Do you still remember that part? Okay. So if I do not have a JL instruction, what am I going to do here? Well, I have to rely on the flags that we have at this point, right? Okay. So if I want to use the flags that we have at this point to basically say, if EAX is greater than 1, I want to go to this label. I cannot use a single branch here. Instead, I would need a sequence of branch instructions, right? So let's think about what is the equation that we need to use in order to determine should we branch to greater than or not. Okay. All right. The sign flag, exclusive or the overflow flag, is basically the less than flag. Okay. This is the same thing as less than. In other words, if sign exclusive or overflow is a 1, it means EAX is less than 1. I'm not looking for exactly the opposite, because the exact opposite would be greater than or equal to. I'm looking for greater than. Okay. So in order to do that, I'm looking for the condition where the sign flag, exclusive or the overflow flag, is a 0. Okay, because that means it is not less than. But at the same time, I also want to make sure that the 0 flag is what? I'm looking for greater than. This is only implying greater than or equal to. I need to rule out the equal to.
That has to be 0.
That has to be a 0, correct. So I'm looking for the sign flag being different from being the same as the overflow, and on top of that, I want the Z flag to be a 0. Is that okay? And if I don't have a JG instruction, which is jump if and only if greater than, then I need to use the existing, the 8 instructions that we have so far, combined with the unconditional branch instruction to implement the same thing. Are we doing okay so far in terms of what I'm trying to do? I want to have a sequence of instructions that can implement the same thing as branch if and only if greater than. And in order to determine whether something is greater than after a comparison, I already worked out the equation. The exclusive OR of the sign and the overflow flag has to be a 0, and on top of that, the Z flag has to be cleared as well. Is that okay? So what do we do here? There are many ways to do this, but the first thing I'm going to do is to rule out the Z flag. If the Z flag is set, I know I'm not going to branch. Okay, so we'll do it that way.
Jump is not Z?
JZ, actually, I want to do a JZ to a continue point, okay? So the continue point is going to be here. In other words, I'm not branching to greater than, I'm just going to continue with whatever is next to this block of code.
Do we have those Boolean operators?
Which one?
Any one of them?
Exclusive OR? Nope.
We have and.
But we can combine branch instructions, additional labels, and stuff like that to achieve the same thing. Okay? All right. So if I have a JZ instruction here, okay, and remember this is just a line of comment because it's not really here. Okay, if I do not perform the JZ because the Z flag is cleared, I have just confirmed this condition here. So now I can check for the rest, which is the sign flag the same as the overflow flag? Is that okay so far? In order for an exclusive OR to be a 1, the two sides have to be different. But since I'm looking for a 0 after the exclusive OR, I'm looking for the sign and the overflow to be the same. If one is set, I want the other one to be set as well in order to branch to greater than.
You can't do an and on the times?
Nope, you cannot. Okay, so the next instruction is entirely up to you, okay? So you can say something like JNO, okay, jump if the overflow flag is cleared, and I'll just go to a particular label, without any, well, I guess I can use this a little bit better. Not overflow, okay. I'll branch to a label called not overflow, and not overflow is going to be here somewhere. And I don't know quite what to do over there just yet, okay? But there's one thing I know if I end up here. What does it mean if I end up here? Overflow is in fact set, okay? Now if overflow is already set and I want the sign flag to be the same to go to the label called greater than, can I do it with one single instruction here? Which instruction would that be? JS, exactly. So a JS here to greater than will take care of one of the two ways, okay? Oh, but what if JS did not take off? What if, I did not go to greater than because the sign flag is cleared?
Well, we know that it's not.
Exactly, it's not greater than,
It's not
okay?
greater than.
Because at this point, I did not go for the NO, which means the overflow flag is set. I did not go for the JS instruction, which means the sign flag is cleared, which means the overflow does not equal to the sign flag, which means, hey, I'm looking for greater than, this is definitely not greater than, which means I have to go to the continue label. So a unconditional branch at this point to continue is going to be okay. All right, so let's say we did take that branch earlier, and we went to not overflow. Okay, so the JNO instruction, in fact, took us to not overflow. So we have now confirmed overflow is clear. What else do I need to confirm to go to greater than?
That sign is clear.
That the sign is cleared, and what is the name of the instruction?
JNS?
JNS, exactly. Jump if the sign flag is not set. And we can now go to greater than as well. And since if I don't branch because of the JNS, it means the sign flag is set. But if I end up here, it also means the overflow flag is clear. So that means they are different, which also means I can just fall through to continue, and that's it.
But, tell me if I'm reading it wrong. But if we get down to where we're going for the JS, we haven't, that means JZ, that means that the zero flag is set, correct? If we get to that J, where we're jumping,
If we go to continue or
so like, okay, so from
the
there.
JNO,
Before the JNO, we only get there if the zero flag is.
we
not
only
set.
get to the JNO
Oh,
instruction
yeah, 'cause
if
it's
the
not
Z
set.
flag is
Not
clear.
set, yeah.
Because if it is set, we just jump to continue right away, and we're all done.
Yeah, you're right.
Okay.
Do you have a command code that we can do just equal to?
JZ,
GZ, which Z,
Jump.
but Z, which means.
there's no
zero,
equal
zero,
to.
zero.
Okay, remember all the conditional branch instructions only look at one single flag to determine whether to continue execution at the label that you specify or the next or the following instruction. That's the only type of decision making you can do in assembly language programming. Okay? Are there any questions about this chunk of code? Well, let's try to present this chunk of code in a slightly different way, and this time we can see if we can kind of visualize this a little bit better. I'm not a flowchart kind of person, but this is kind of one of those rare occasions where a flowchart may come in handy. So we'll basically say, okay, here's a JC instruction. A JC instruction is a branch, okay? Because there's one way to come in, and there are two ways to get out. Does that make any sense? So one way to get out, which is the side one, is when the condition that I'm looking for is true. In this case, Z is 1. The Z flag is set. I'm going to hide all the pens that are running dry, so I'm not going to retry all of them, right? Okay, so, and this one is basically Z is clear. But if Z is clear, I'm not going for the branch. And this one, will go to continue. So I'm going to put a label here, which is continue, and there will be multiple ways to get here, okay? And we'll see that there are multiple branches to go there. The next instruction is JNO. JNO is a diamond because it is also a decision to make. JNO. As the name implies, it means we are going to branch when the overflow flag is a 0. Okay? And this time, if it is a 0, we go to another label called not overflow. So we'll just go to a particular label here, and it is not overflow. Okay. If I continue execution, that means the overflow flag is a 1. Is that okay? So if I ever end up here, I have confirmed two things already. The first thing I have confirmed is the 0 flag is clear. The second thing I have confirmed is the overflow flag is a 1. But what I'm really looking for is the sign flag and the overflow flag being the same. Because that's the only way to make the exclusive OR being a 0. Okay? So the next instruction is JS. So here's another diamond here. Is JS. JS says, I'm going to the label as specified when the sign flag is a 1. So if I follow this branch, I have come through this part, through this part, through this part. I have just confirmed that the 0 flag is clear, the overflow flag is set, the sign flag is set, which is the proper condition. So over here, we can go to that label called greater than. Well, what did we fall through this? If we fall through that, we go to the unconditional branch instruction, which does not ask any question, and it just goes to continue. So I'm going to make a loopy here. Yeah, that's why I don't like flowcharts. But this is not actually a loop, it's just, fine. I'm gonna fix that in case someone thinks this is actually a loop. It's an on-ramp, okay? I like those on-ramps, especially on a rainy day. All right. Now what do we do at not overflow? Not overflow is the fourth line from the bottom on the screen. So the first thing we do after we get to not overflow is another diamond, right? That's JNS. Okay, let's figure out how we got here. We got here when 0 is cleared, when overflow is cleared. So by the time I get here, I know the 0 is cleared, overflow is cleared, and I will go to GT if and only if the sign flag is also a 0. Okay, so that means this branch, which is say the sign flag is a 0, is okay to end up here. Is that okay? But if I fall through, which means the sign flag is a 1.
You should fall up, because you're going
All
to get right
false.
to continue.
How about?
You fall forward, because you'll just
But
get
I
right to
labeled the
continue.
branches. But I labeled the branches, right?
It was too late, we've gone too far.
We've gone too far, exactly. So if we fall through this one, which means we go to the continuation because that's just falling through.
Yeah.
Oh yeah, that's going to be ugly.
Yeah, but just go
Okay,
out.
fine. That's why I don't like flowcharts. Okay, but what does it mean when we end up at continue? It means that the overflow flag is cleared and the sign flag is set. Well, that's okay because that means it's less than in sign interpretation. So we should go to continue because I should only go to GT or greater than once I confirm the second operand is greater than the first operand in the compare instruction. Is that okay so far? Well, can we test this code? I mean, it looks questionable. Can we test it?
Sure.
We can test it, right? So this is what I'm going to do. I will test it. I mean, testing code like this, okay, is a big part of what you need to do in this class. Okay, this is not a class where you can just kind of read stuff and think that you would be able to absorb all the material. If you do it, using GDB and go through the debugging process, at least with myself, that's how I would consolidate everything that is in theory and actually learn and go like, okay, now I confirm that this is actually the way it is. Okay. So I would do, a little program with everything that I learned in this class. So I would just write this program and tweak it also, okay? What I'm trying to do is to implement a single instruction called JG. But I'm assuming the JG instruction itself does not exist. I will rely on a sequence of instructions in order to accomplish the same thing. So that's why I'm gonna name this program JG.S because it's really just trying to implement the same thing as the instruction JG if that instruction existed. Okay, when you spell global, there's another way to spell it. If you spell it without the A, it will still be accepted. And that's because programmers cannot spell. Especially the first few programmers who could not spell. But since by that time, a bunch of programs has already been written using global, the misspelled version of dot global. Whoever was making the standard decided to go like, okay, we'll take both. It's kind of like bunny versus bunny. Since I released the specification with bunny, and some of you, actually made the correction to bunny, now I have to accept both standards. It's the same way here. You can spell global without the A, and it is still considered correct. All right, so we have a program like this. And what we'll do is we're going to move some constants here into EAX, and then we'll compare it to another constant here and use the sequence of instructions that we just talked about, JZ to continue, JNO to not overflow, and then we have another JS here to greater than, and a jump to continue here. And here is not overflow, which has a JNS instruction to greater than. And then here we have the continue instruction. And to confirm that we end up here instead of somewhere else, we put a no op instruction, okay, just as a quote unquote marker that we end up here instead of the other place. And then the other place, which is called greater than, is going to have its own little marker no-op instruction. Because this way we can see that we actually went to the continue label and not to the greater than label by accident. Because otherwise, if I do not have the no-op instruction on line 14, the two labels are basically the same. So we cannot tell how we got there. This way we can definitely tell. If we get to the no-op on line 14, EAX should be less than or equal to the first operand. If we end up on line 18, EAX should be greater than the first operand. Yep. Go ahead.
If we were to write this ourselves, would placing some like arbitrary value in either one of the registers be default instead of using no op, like we just said, all right, if it's greater than, I'm gonna put 15 into EAX, and if it's continue, it will still be the same, right? Like,
When you jump to
Yeah.
the label, then you just add something to the register.
okay, so
Right.
but it wouldn't change the logic. It wouldn't use anything to logic.
Correct. Now the other way to make this program even more flexible is to change this one to EBX. So now I can just compare the two registers on line 5. And the cool thing about doing this is I can delete the instruction on line 4, replace it with a no-op instruction. And then I can, in GDB, I can now say, set var $EAX equal to something, set var EBX to something. Then I can reuse the same program without reassembling whatsoever to test multiple test cases, okay? So I'm gonna do it that way. So I'm just, changing this program, get rid of this one, change it to no op, okay? So this program is totally senseless if you're trying to run it all by itself. In fact, it will crash because it doesn't have the proper exit code that we normally need to have at the end of a program. It only makes sense when you run it in GDB and put breakpoints on line 14, line 18, as well as line 4, okay? Because the only purpose of this program is to test whether this sequence of instruction is doing the same thing as JG, jump if greater than. Okay? All right, so let's go ahead and give it a try. G stabs -o jg.o jg.s ld-o jg jg.o gdb jg. For those of you who are interested, you can actually write a script to do this. Okay, you can. Whatever you type inside GDB as an interactive command, you can put those commands into a file, and that becomes a script that GDB can read and execute stuff autonomously. Okay, and that can really help with your homework assignment, because instead of having to remember how to use restore, the breakpoints and stuff like that, you can just put everything into a file, okay, and you can just run it from the command line. The way to run it on the command line is to do a GDB name of the executable less than, which is the redirect symbol, and then the batch file or the script file for GDB, and it will automatically run all the commands that you specify in the file. Okay, so it comes in pretty handy. But this time I'm just going to run it by hand. So I'll put a breakpoint on line 4, put a breakpoint on line 10, and then put a breakpoint on line 13. But instead of saying line 13, on line 18, oh, wrong line. Delete the second breakpoint. Put a break. That's why it's easier to use label names. Break at label continue, break at label greater than. Okay, you can do the same thing too. So this way, it is not sensitive to the line numbers anymore. It makes your script a lot more flexible because you can just say, hey, I want to stop at a particular label. If you insert additional lines before that label, it doesn't change it. Okay, so that's kind of a cool thing to do. I could have done the same thing with underscore start. Okay, break at underscore start. Run the program. Now I'm at the no op instruction. That doesn't do a single thing. So what I'll do is I'm going to say set var, set variable. EAX is going to be, what do you guys want to test first? Because we have literally 3 test cases: less than, greater than, and equal to. Which one do you guys want to test first?
Less than.
Less than? Okay, so we'll make EAX less than EBX, which should end up at the label continue, right? And we'll make it special tricky, okay? So we will make EAX a -1. Now this is tricky because -1 is a signed interpretation of the 32 bits in EAX. And the bit pattern of -1 would be 32 ones as a binary number. So if the interpretation is incorrect, that will be interpreted as 4 billion something, which is certainly not going to be not going to be less than EVX, because you can observe how I set up EVX. So that's the first one, and EVX is going to be set up as just 1, which is 31 zeros as most significant bits, and then 1 single 1 as the least significant bit. So this forces me to make sure that the sign interpretation is correct, because otherwise it would definitely do the wrong thing. So now we can do a continue, and it stops on line 14. And if you remember, line 14 is the no op after the continue, which means it did make the right decision and end up at the label continue instead of greater than. Is that okay? So now,
was the second operand, right?
sorry?
EAX was the second operand?
Yes, EAX is the second operand. When we use comparison operators, we are always relating the second operand to the first operand. And that's why it's kind of tricky, because you have to read it backwards. Let's try equal to, okay? That's the second test case. So we'll basically rerun the program from the beginning, which will stop at the first breakpoint. Set var EAX to 45, set var EVX also to 45. So this time they are the same, they equal to each other. Continue execution. I should still end up on line 14, right? Because equal to is not greater than, and I ended up on line 14, which is good. Run the program again. This time I'm going to test greater than, and once again I'm going to be tricky and use the sign thing, okay? So it's not as straightforward as without the sign interpretation. So I'm going to set EAX to 1, okay? And I'll set EVX to -1. 1 is definitely greater than -1 in the sign interpretation, but when you look at the bit pattern, 1 is basically all zeros and then a 1, and then -1 will be all ones. So if I misinterpreted the signness, this will definitely end up at the wrong place. So I set up both registers, continue execution, and this time it ends up on line 18, which is the no op after the greater than label. So it does work. Okay, so as far as we can test up to this point, the code does work. Yep.
Do you have any control over the interpretation? Can you set it so that it would interpret it?
That is the fun part of assembly language programming. The interpretation is based on which flag you pay attention to. That's it. If you pay attention to sign and overflow, you're using the sign interpretation. If you pay attention to B or C, your borrow and carry are basically the same flag, then you're using the unsigned interpretation. That's how you choose the signedness of your numbers, which is completely opposite or reversed compared to C and C++ programming. In C and C++ programming, the type of the variable determines how you interpret the bit pattern. In other words, if you say int x and unsigned y, then we know that every time you use x, it is going to use the signed interpretation. Every time you use y, it is going to use the unsigned interpretation. It is exactly the opposite in assembly language programming. The data storage itself has absolutely no type affiliation. It's just a whole bunch of bytes. A register is nothing more than 32 bits. It's not signed, it's not unsigned, it is not a pointer, it is not an integer, it is not 4 characters. It is just 32 individual bits. But when you compare, it becomes a number. But it doesn't tell you whether it is signed or unsigned. Because if you remember, the subtractor circuit that we did not even care about signedness. Because 1 minus 1 is 0, 0 minus 1 is 1 with a borrow of 1, and that sort of thing has nothing to do with whether it is signed or not. It is just a bit pattern manipulation. The same thing applies to the compare and the subtraction instruction. Whether it is signed or not is determined by the conditional branch instruction. When you choose to use JS, JO, JG, JL, then you are using the signed interpretation of the compare. If you use JB, JC, then you're using the unsigned interpretation. Are we kind of doing okay so far with that concept? Because you really kind of have to remember that part. It's hard to undo it because with C and C++ programming, you remember, okay, the type of a variable is attached to the storage. It is attached to the variable itself. Not so in assembly language programming. Okay, data has no type. It is only when you use it, then you are choosing a way to look at it. Okay, are there any questions about this part? Okay, if there are no questions, I think most of you will be terribly disappointed when I tell you that the JG instruction actually does exist.
I was like, you said JL.
Yeah, so JG does exist, JL also exists. In fact, and we also have some other instructions, okay? So JB and JC are the same, they are for unsigned interpretation. JB can be read as jump if below, okay? So below is kind of like less than, but it's not exactly the same. Less than is signed. When you use L or G, it is signed. When you use B, it is unsigned. But we also have JA. JA is jump if above, which is related to jump if below. It is for unsigned comparison. Are there any questions about JA, JB, JC, JG, JL, JNL, JNG? No. JNA, JNB, jump if not above, jump if not below, JNL, jump if not less than. Yep.
JG is signed?
JG is signed.
Okay.
Because we pay attention to the overflow and the sign flag. So this is a good time to go back to the notes just to show you where you can find additional information about all of these. I would call these compound jump instructions because they make use of multiple flags. But it is here. Follow that branch. Go to here. Nope, not that one. Probably before that. So maybe here. There we go. So we have the JL, JNL, JG, JNG, JA, JNA instructions, and the explanation is down here. JL will jump if and only if the exclusive OR of the sign and the overflow is a 1, and JG is the one that we just implemented, and it is documented here to be branching if and only if the Z flag is clear and the exclusive OR between the sign and the overflow is a 0, which is exactly what I just wrote on the whiteboard. So you might want to look at this one here and just pick 1 or 2 as an example and say, if I'm only given with the basic 4 pairs of branch instructions and the unconditional branch, how do I implement every single one of these? Okay? And then you can push yourself one step further. What if you are not only, what if you don't even have J and something? Okay, so you only have J, C, JC, JS, and JO. So without the negated version. I mean, you can always do it, okay? It's just more complicated without the negated version. So those would be kind of interesting exercises that you can do kind of by yourself, okay? It's not going to be graded, but it really helps to understand, what is going on with this stuff. All right, so here's another word on cisp versus RISC. With a cisp architecture, these are the only 4 instructions necessary. Even the unconditional branch instruction is kind of extra, because you can always say, if you want to implement a unconditional branch, a JMP instruction, you can always just pick one of these 4, okay, and say JC and then JNC to the same label. Then it will, regardless of the flag status, it will get to the label. But if you're only given with these 4 instructions, then you also need the unconditional branch instruction to finish the whole combination. Are there any questions? If you are going to design a pure RISC architecture, then you will only have these 4 plus JMP, and that's enough to implement everything else. Yep.
So this is sort of a general question, but with the JMP, I mean, I know GoTo is really, really frowned upon. Is JMP still think it's okay to use that?
In assembly language programming, that is the only thing you can use. To implement a loop, that's the only thing you do. Even in a conditional statement with an else and a then, you still need an unconditional branch at the end of one of the branches. We'll illustrate it later today. Yeah, I think we'll get to it. But it is okay. The answer is yes, it is okay in assembly language programming because we don't have structured code at all in assembly language programming, which is good and bad in a way. Okay, for people who have a tendency, despite C and C++ being a structured programming language, if anyone has a tendency to write spaghetti code, he will get really, really bad in assembly language programming because there's no structure in the language itself. Okay, but if someone has a tendency to write code in a structured way, regardless, then this is not a big deal because you can still write structured code even using jump instructions. It's just how you think about it and how you write the code that makes it structured. Are we kind of doing okay so far with that concept? Yep.
Check the recorder.
Check the recorder. Yes, I will do that. And the other one. Nope, it's the first one. It's still going, and let me see whether the level is still good. It is still going. So thank you for the reminder. It seems like it's okay at this point. It's just the first few seconds that has some complaints, which is kind of odd. I hope it's not the drive dying on me. That can happen too. I have killed many drives already in the past few years. Yeah, USB thumb drives are easy to kill. Hard drives are much harder. They're much more robust. All right. So, are there any questions about the conditional branch instructions? There's no questions. All right. So we can move on to something that is more interesting, which is down here. Not division and multiplication. We can skip that one. Now we move on to control structure. In other words, given all the cool stuff that you can do in C and C++, how do we do all of that in assembly language? Well, there has to be a way, right? There has to be a structured, mechanical way to do that translation, because that's what a compiler does. So with these two sections, what we'll do is I'm turning every single one of you into an organic C compiler. Yay, we can now compile programs without the compiler. Okay, but I'm going to do it with a structured way, which means it's going to be mechanical. Whenever I have a choice, I would go for the newer notes, okay? But for those of you who want to have some extra material, you can refer to the older notes as well. It's going to be the same thing. It's not going to be conflicting. It's just presented in a slightly different way. So I would go for the newer note, okay? Which is, there's a reason why I rewrote that stuff, right? Usually it's because I was bored, but sometimes it's some other reason. Okay. So the purpose of this module, okay, I tried to write the purpose of each module. So the purpose of this module will contain the mechanical instruction so that if you are given a regular C, C++ source code, you will have the method to break it down in a very mechanical way into assembly code. That's one of the things that you should understand in this class is how do I break it down into really small mechanical steps. So next section talks about the three types of statements that we have in C and C++. The first one is a conditional statement. So in this case, I give you kind of like an abstracted conditional statement, where I don't spell out the condition, I don't spell out what is the then block, I don't spell out what is the else block. I'm just saying that there's a chunk of code corresponding to block, another chunk of code, block 1, another chunk of code, possibly empty, corresponding to block 2. Because if you have a conditional statement that has no else, you simply have an empty else statement. Okay, it's equivalent to having an empty else statement. What about C as a condition? Well, we don't need to know what it is, okay? Because what I want to do is to turn this structured code into unstructured C code. So functionally speaking,
Unstructured C code or
unstructured.
Assembly.
I'm taking that structure away from the regular C code. So if you are given a template, a chunk of C code that looks like this, is it equivalent to this C code here? If you're not familiar with goto is basically a unconditional branch. Okay, it's an unconditional jump instruction. And then L1, L2 with a colon is the definition of the loop. So are they the same? In other words, do I get to block 1 if and only if the condition is false?
No.
It's true, sorry. If and only if the condition is true, I end up at block 1.
You'll always end up with block 1, right? Because-
No, there's a go-to, there's a possibility I might go to label L1.
Well, I mean, yeah. Well,
Yeah.
you get, but what I'm saying is, okay, well, if it's not, then you'll go there, and if it is, you'll get that block.
Yeah, go ahead.
Don't you go to block 2 either way if it's code?
Nope. I do not, because after block 1, I have an unconditional go-to to continue execution
Oh,
of
I
L2.
see.
So I branch around the else block after the then block. And that's why you need to have the unconditional branch instruction in assembly language programming, because that's the only way you can get around something all the time. But are there any questions about this? Are there any question about how the structured code is functionally equivalent to the unstructured code? Now, obviously, if you turn in any program in cisp430 or 400 using gotos and labels, I'm not going to be responsible for the result of doing that. Okay, even if you can say, but tag set is equivalent, functionally it's equivalent. Okay, I cannot say anything about how the other professor will grade your homework if you use this kind of flat code.
Why we couldn't use goto? A lot of tools use goto.
Huh?
A lot of tools can use goto. Why we couldn't use UC?
A lot of what?
A lot of languages use goto. Why
A
we
lot
can't
of
use
languages has the construct of goto, but when you are not doing it in this context, the goto word is a taboo.
Bob says it's the G word.
It's the G word, exactly. In fact, it's much worse than the F word in a conversation, because the G word will mess up things not only at that moment. It is down the road. Things will get really, really ugly, and real fast too. I have personally seen source code in the order of. I have seen a single function with more than 500 lines of code. And I'm not exaggerating, okay? This is from my previous job before I started teaching. And within that 500 lines of code, which is bad enough to begin with, there are go-tos. Now, sometimes, go-tos are bad, but it's like, well, I guess it's kind of understandable. There are better ways to do it, but I guess, in a pinch, this is not really, really bad. Like you have one single label at the very end of a function, and if in the middle of a function you encounter a condition where it is not recoverable, okay, and you're dealing with C and not C++, there are no throw and catch statements, then you really don't have a whole lot to do, okay, except to go all the way to the end, return an error code, and you're done, okay? Yep.
For some loops, actually goto is very useful. Just get out there, go to where you want to go. That's it.
Just
It's
remember
very
this:
useful.
if you're not writing code in assembly, do not use goto. I'm not going to argue. To me, this is more than a religion. Okay? It is more than the truth. Okay, this is the golden rule. Okay, do not. Well, I guess golden starts with a G too, but but this is the rule. Okay, do not use goto unless you're writing code in assembly language where you have no choice. Okay. Okay, but the first part is, is everybody convinced that this code is functionally really the same thing as this code? No? How is it not the same? Under
I
what
didn't-
condition is it not the same?
I didn't get the part like how to go to L2, then change label 2, then label 1.
Yeah?
So like after go to L label 2,
You mean here?
yes,
Then it will end up at this label.
yes.
It will branch around block 2. It's jumping around the entire block 2. Is that okay? You can draw a picture. I mean, if you draw a picture, it will help convince you they will do the right thing. Yep.
Part of the confusing part of it is just because the condition itself gets reversed.
Yes, it is reversed.
Is it possible to flip things around and change the condition, or is this
You
really?
can, but this is the way to do it. But as far as the compiler is concerned, this is the way to do it because the compiler is still reading your program from top to bottom. So the compiler will encounter block 1 first. So if you try to do, well, I see your point. If you say if C go to L1 and L1 is right before block 1, and then you have an unconditional branch after that, you can do the same thing. But this is the more efficient way to do it. You are basically minimizing the number of branches doing it this way. But the other way I can see, you can do it the other way too. But putting a negation here is going to be okay as well. Right, and then depending on what is C, the negation may not even be difficult to deal with, because if it's a comparison, you can always flip the comparison itself. Yep.
There's no actual go-to in assembly, is there? Go-to is actually this jump in assembly, right?
Yeah, go-to in C is the same thing as JMP in assembly. So by doing this, I'm really trying to, step by step, I'm trying to reduce statements in C and C++ into things that we can easily do in assembly. The second part deals with a conditional statement with no else. Okay, so we just have a condition and a block, and then block of code to execute. Then it will be the same as this one here, because we are going to branch around the block 1 if the condition is false. Okay, that's it. There's nothing to do when the condition is false. So are there any questions about this code here? I call this the flattening of C++ code because what we are doing is we are removing the structure in C code. And you have to do that when you're converting C code into assembly code because assembly code has no structure inherently. So you have to remove all the structure. Okay, if this is okay, we're going to move on to a loop. Okay, the first one is a pre-checking loop, which is known as a while loop in C. So the first chunk of code is while C block 1. Okay, we are kind of familiar with this kind of code. The second chunk of code is removing the structure. You can see the curly braces are all gone. And I want you to kind of confirm that the second block of code is functionally the same as the first, except it doesn't use the word while or use any type of structure. Instead, it relies on go-tos and labels to control when do I branch and where do I go to. Okay? So let's just double check. Okay? With the first chunk of code, it means as long as C is true, we will do block 1 and then go back and check C again. Right? So we'll keep doing this until C is no longer true, then we go continue execution after the loop. With this code here, the first thing we do is we check C, but we are checking the negation of C. If the negation of C is true, then we go to L2, which is after the loop, because it doesn't go, there's no way to go back to L1 at that point. So we're exiting the loop when C is not true. Is that part consistent with a while loop? Okay, the second part of a while loop is after you perform block 1, we have to go back and check C again. So in the flattened code, I have block 1 here, which means if C is true, then not C is false, which means it's not going to go to L2. Then it will fall through to execute block 1. After block 1 executes, I have an unconditional go-to to go back to L1, which basically forces execution back to evaluate the condition and see if it is time to exit. So is that enough to convince you guys that the second block of code is functionally the same as the first, except we don't use the while word anymore?
It's kind of nitpicky, but the go to L2, should that be a semicolon after another colon?
That is true, it should be a semicolon. Very good.
Oh, you copied the L2? Or did you just type it like that?
No, I just mistyped. But in terms of the meaning of the code, are there any questions about the meaning, not the syntax?
We're just giving you a hard time.
That's
Low
okay.
charts.
That's okay. It's right before the break, and I'm ready for that.
It's like right before I finish grading your stuff.
Are there any questions about this code here? Yep, go ahead.
So we're going to a part where we got like an intermediate code in between like C and assembly. Do you show like the final assembly code for?
Oh yeah, I have one final thing to illustrate the whole process.
Okay.
Yeah, but this is just one step. Now I cannot give you one complete instruction because it has to be structured like this. Because you can have a conditional statement inside a while loop, which is also itself inside the else of a conditional statement, which is inside the do loop, right? So I can only give you instruction to break one level of structure at a time, and you will have to look. Once you're done with this step, then you look into block 1 and figure out what block 1 is. If block 1 is a conditional statement, do the trick with conditional statement. Break it down. So you have to reapply these techniques, quote unquote, recursively until you end up with completely flat code with no conditional statements, no loops. Okay?
Is that kind of what compilers do?
Exactly, that's what compilers do. And that's why I said earlier that I'm turning you guys all into organic compilers. And this is a post-checking loop, which is rarely used in C and C++ programs, but there are occasions where it is useful. So the only difference is we have to perform block 1 first, okay, and then we check the condition. If the condition is true, we go back to L1. So this turns out to be the easiest one to flatten because we just have to define a label, perform block 1, and then have a conditional go-to to say if condition C is in fact true, go back to L1. Okay. Now this kind of stuff is really easy for me, not because I have done this a whole lot in my previous job, but it's because my first programming language was AppleSoft Basic. Yes, you use that in the original Apple II computers.
Isn't that a Microsoft language?
It is a Microsoft thing, yes. But in that particular version of BASIC, the only thing you can do with a conditional statement is to control where it goes to, where to go to after the then. You cannot specify a statement. You can only specify then go to blah, blah, blah. So that's why this stuff is really familiar to me. Are there any questions about this part? We are done with control structures. Yay! But what about for loops? Well, a for loop is a while loop, right? It's a while loop with a initialization before the while and the post operation at the very end of the body of it. What about switch? Switch can be seen as a nested conditional statement with multiple equal to. Okay, that's a switch statement. Are there any other control structures in C and C++?
Isn't if a control structure?
Yeah, but we dealt with that. What we're doing is we are converting all the conditional statements, if, into a condition and a label to go to. So we are not allowed to have a then statement anymore. It's not a general statement. You can only do a go to as the then portion, and there's no else that we can use. Okay? And you will see why I want to break it down this way. Okay, but first of all, this you can do without an assembler. Okay, in other words, if I give you structured code in C, you can apply all of these tricks here to a particular program and then test the program to make sure it is functionally the same as before. Okay, so there's no actual assembly language programming in any of this instruction. But here's the next question. What if C is a complex conditional condition? So it involves disjunction, conjunction, negation, and a whole big mess of that stuff. What do we do in that case?
We fit everything that we've just done together.
Well, not quite, okay? Because it's not the same thing. If you have a compound logical operator as the condition, you kind of have to break it down further into more but simpler conditional statements where you have a if some condition go to a label. Okay, that's what we're trying to do. So the next few slides will demonstrate that part. So we go up and down again. Conditional go to and Boolean operators. So how do we deal with a not? Well, this is how we deal with a not. Okay, in general, if you have a not C as a condition, not a particular condition, C go to label L1, what you can do is to get around it, okay? So so now we are, in the second block of code, we got rid of the negation operation, and the sacrifice is we have now more labels and go-tos. But if you look at functionally speaking, is these two blocks of code functionally the same? If the condition is not true, we go to L1. Does the second block do exactly the same thing?
Is that true if we just put like GZ there, is that true will be 1? The value will be 1?
Okay, question is, in the first block of code, I want to end up at L1 if and only if the condition is false. Otherwise, we continue execution with whatever is next to this. Okay? Is it doing the same thing in the second block of code?
I didn't understand the second line. I got the first one. If it's not true, so go to like else statement.
Mm-hmm.
What's that go to L1?
That's the next statement. If C go to L2 semicolon is the entire conditional statement. So the go to L1 is not a part of the conditional statement. It is a statement that is sequential to the conditional statement. Is that part clear?
What kind of case will they go there?
Sorry?
How can they go to
L1?
Yeah.
When
that
C
false?
is not true? See, when C is not true, we obviously is not going to go to L2, right? Because that's the then statement of the conditional statement. So if we're not going to L2, where are we going? We're continuing execution.
L1.
What happens when you continue execution? You execute go to L1, so we end up at L1. So when C is false, we end up at L1, which is exactly the same thing as the original code. With one exception, the negation is gone.
So I think it's the same line of what you were answering with this. What again is the benefit of, in this case, not checking the negative value of C?
Because the C itself can be a really complex, big mess of conjunction and disjunction thing. So by doing this, I am reducing the number of operators that I cannot do in assembly language programming. Because there's no negation, there's no logical negation in assembly language programming. So I have to get rid of all of these things that I cannot do in assembly language programming. I can compare, but I cannot negate.
Oh, okay, so actually, our last examples where we have if not C, what's inside of that is actually this.
Correct.
Because we don't actually have a not C.
Because in assembly, the only tools we have is compare. I'm not even going to specify the width because that depends on what you're comparing. So we have compare, and then we have all the conditional branches. But the conditional branches are very simple, okay? If the carry flag is set, we go to a particular label. If not, we continue. Does that sound familiar to you?
Yeah.
That's why we're doing it, okay? So we have JC, JNC, JZ, JNZ, and so on. So I'm trying to reduce everything that we can express in a control structure in C and C++ into this kind of operation. Well, we obviously, the JNP structure is useful as well because that's our go-to. Are there any questions about slide 4.1? Basically getting rid of not. Going once, going twice. This is good. All right. We only have like 3 more slides to go and then we're all done. Completely done with control structure. So this time we get rid of or, okay? If condition C or condition D, we go to label L1. That's the original structure. There's no way for me to do logical or as an assembly language instruction. So I need to get rid of it. And the way to get rid of it is to make the control structure slightly more complicated, right? So in the original instruction, it is saying if C is true or D is true, we go to L1. C and C++ as a part of the language definition itself uses short-circuited evaluation. And hey, if you look at the second chunk of code, doesn't it do the same thing? Okay, the first line says if C is true, we go to L1. Well, what if C is not true? We fall through to the second statement. So we have a second chance to go to L1 if and only if D is true in this case. So if C is true, I don't even bother to evaluate D, which is also the behavior of C and C++.
And that's literally why it's short-circuited, because of the way the assembly comes out?
I'm not so sure about that part, but I think it's because, remember, the C and C++ language was invented in a using a reverse reasoning compared to most other programming languages. With most programming languages like Pascal or Ada or anything like that, people start with an objective and say, we want the best high-level programming language for programming, defense, weaponry and stuff like that. That's the case of Ada. Or we want the best programming language to illustrate concepts in programming for instruction. That's Pascal. Okay. C is exactly the opposite. The two guys who originally wrote Unix probably wrote the operating system completely in assembly code for a few days and then got completely bored and go like, oh, we cannot do this anymore. Okay? And they invented the language more or less as a macro to make things easier and quicker. And that's why they look at this code and go like, hey, short-circuit evaluation makes more sense, right? And that's why the programming language is the way it is. That's why we have pointers. And that's why you can do all kinds of funky stuff with pointers in C and C++ where no other programming language can even come close. It's because of the heritage of coming from assembly language programming and not so much from other perspectives. Okay. And the next one is AND. I think that's the last one, okay? Because we only have three logical operators in C and C++. This is the last one. So the original code says if C and D go to label L1. So we evaluate condition C. If it is true, we evaluate D also. And if both of them are true, we go to label L1. You look at the second chunk of code, is it really doing the same thing? This one looks a little bit awkward, but it really is doing the same thing. Because the first thing it does is to check C, but with a negation. So if I can confirm that C is false, don't bother to evaluate D, just continue execution with whatever is next to it. On the other hand, if C is true, which means not C is false, then we fall through the first conditional go-to statement. We go to the second one. If the second one confirms D is true also, then we have reason to go to L1. If C is true but D is false, then we still fall through to label L2, which is exactly the behavior of the original code. So this one is kind of a trade-off. We got rid of the conjunction, but we end up with one negation in this case. Are there any questions about the reduction of logical operators into just conditional statements and more go-tos and more labels? Are there any questions about this? And I just want to emphasize again why we are doing this. It's because in assembly language programming, we don't have logical not, we don't have logical and, we don't have logical or. But we do have go-tos. We do have conditional branch instructions, and we do have labels. And that's why I'm just slowly and gradually in each step, I'm reducing the number of things that we cannot do in assembly and do more of the things that we can do in assembly. So if you keep going like this, eventually what do you think the conditions will boil down to? Look at any C program, okay, and look at the conditions inside a conditional statement or a loop. What do they eventually boil down to? Comparisons. They all boil down to comparisons, okay? Can we do comparisons in assembly?
Yes.
Yes, we can.
No.
Yes.
Can we look at the result of a comparison and confirm, is it less than, greater than, or equal to? Yes, we can.
Yes.
Okay? Gosh, I'm starting to sound like a politician. Yes, we can. Not a good sign. All right, so the last part is a simple reduction, which means in certain cases, we can do the reduction without using those tricks. So this is just an example. It is not the case that x is greater than or equal to y. There's no need to apply that rule to make it more complicated, because in this case, instead of confirming it is not that x is greater than or equal to y, I can just confirm that x is less than y. Okay, a whole lot easier this way. In the second one, I'm combining x is less than y or x is greater than y to just x is different or not equal to y. So there are things that you can do to optimize that you don't have to go through the entire trouble to go through all the mechanical steps. Okay? In writing a compiler, this sort of thing is called a peephole optimization technique, because you're basically looking at a small chunk of code and say, hey, I recognize this. And I can do this with this little simple structure here instead of exploding it to something far more complicated. You can obviously also utilize De Morgan's law. Okay, if you have a negation on the outside and a conjunction or disjunction in the inside, you can apply De Morgan's law. Okay, because De Morgan's law is kind of distributing the negation to the component inside the conjunction or disjunction, but you have to change the conjunction to a disjunction and vice versa. Okay, so there are techniques where you can use and not to rely on the mechanical way to do it, but the mechanical way is always going to work. Okay, this is just going to make it easier. All right, and we have just a few minutes to go. Comparisons in general. Okay, so in comparisons in general, this is what we see in something. Okay, so I'm assuming y is something that you can compare with, and x is also something you can compare with. So one can be a register, the other one can be immediate. I don't really care. Okay. So the way you read this combination, these two lines, is to say if x are y, then we go to label L1. That's how you read it. I know it's really awkward because you have to read it backwards twice. Okay, because the first backward is the branch, and then the second one is reversing x and y. So once again, I'm going to say again, these two lines of code means if x are y, then go to L1. R is a relation. R can be equal to, less than or equal to, greater than or equal to, okay, or not equal to. So whatever R is just a relation. Is that okay so far? Once you get used to reading this the right way, it makes it very easy to implement code in assembly.
Can you repeat that one more time?
If the relationship they go continue, otherwise.
Okay. This line of code in C or in pseudo C is the same as these two lines of code in assembly. Okay? Yeah, because the reason why we have to spell out x and y backwards is because in compare, we subtract y from x. Okay, and that's the reason.
Is that GR means?
Huh?
GR.
GER?
No, the second command, GR.
JR? No, this R is a placeholder. This R is the same thing as this R here. So if that R is not equal to, that R is NE or NZ. If this R is less than, then this R is either a B or an L, depending on whether it's signed or unsigned. Is that okay? Well, I think we are all set up. Man, I should have given you one more homework assignment before the break. Okay, so what you want to do, okay, see, so here's the thing, okay, I spent all this time to type up my notes, so you are going to read it. And I know you can break next week. This is the code. I have no idea why the code is structured this way, okay, or what it is actually doing. If this is the original C code, then you go through the process of translating it one step at a time. So the first step is, well, I usually just comment everything into comments, and then you just take one control structure at a time and change it into assembly code. So when you look at this code here, it's just doing it really one step at a time. So if you have the time to read this, it will explain to you how to apply the techniques, the transformation that we have talked about in the previous slides, one step at a time. The only part you have to be extra careful about is the use of labels. Okay, because if you misuse a label, if you use a label from before and it's not the right label, and you go to that label, the assembler cannot check that. Okay, so you have to be careful with the use of labels. But other than that, the process is really mechanical. It's really just step by step. And the trick is to do it one step at a time. Don't try to read a chunk of C code and convert the entire C code into assembly. Just do it one at a time, okay? Are there any questions about this? Do you think this might have something to do with your homework assignment? Maybe, right? I mean, if you can specify your code for the homework assignment in C, you can apply all of these techniques and convert it into assembly in a really kind of mechanical way. Okay? You don't really have to keep stuff in your head. It's just doing it one step at a time. All right.
You have the next test. When will the next test be?
The next test is going to be the second week after we come back from the break.
When are you going to give the my practice?
The practice test is going to be in the week right after spring break.
When you release before the break spring. When you release before spring, somebody can find the time to read it.
But I only have today and tomorrow before the spring break.
You just release it.
I don't think, well, I can give you what I used last year.
Yeah.
But that may because I reordered the topics a little bit, so that means what I have covered up to this point last semester is not going to be the same place as where we are here.
Okay, so we can study. At least we can study something.
We can study. I mean, everything that we talked about up to this point is a part of the scope.
I like more practice questions, not more works for me.
Take a look at all your homework assignment in C and C++ and convert everything into assembly.
I don't know how about that.
No. Just work on simple stuff, and convert those into assembly code. Give yourself some homework assignments.
More close to test.
Give yourself some homework assignments.
Yes. Write the code to find the maximum of 3 variables in C and C++, and then convert it into assembly code. So if you are given 3 variables, W, X, and Y, I want you to find the maximum and store that into Z. Do it in C first, okay? That's not difficult. But once you have the C code, convert it into assembly code. That's a pretty good test. Or you can say, while X is less than Y, increment Z and increment X in the while loop. Do it in C first, convert it into assembly, and make sure your assembly code will do the same thing. So, there are many examples you can come up with, just
so
regular
like
C
assign,
code.
I have that.
So use a 3 variable X, Y, Z, and give
Find-
them a value and
find-
check
find the
which one is the
maximum.
maximum.
Yeah, and in assembly code you can just use register EAX, EBX, ECX, and EDX,
Then
right?
compare.
And then compare instruction,
Yeah.
conditional branch instructions. But then you also have to say, okay, are we using signed integers or unsigned integers? Just assume some, one way or another, okay?
Why do we need to check it sign or unsigned?
It's
Why
just
do we
for
need to check it
practice.
sign or unsigned?
You have to decide how you want to do it. I mean, that's entirely up to you. It's an assignment to yourself.